Welcome to this coding walkthrough. Today, we'll tackle problem number 506, relative ranks. This problem challenges us to assign ranks to athletes based on their scores efficiently. We'll explore the problem statement, break it down step by step, and analyze our approach. Let's get started. In this problem, we are given an array called score, which contains the scores of n competitors in a competition. The goal is to assign ranks to these competitors based on their scores. The ranking system works like this: the highest score gets the rank gold medal, the second highest gets silver medal, and the third highest gets bronze medal. For the rest of the competitors, their rank is determined by their position in the descending order of scores, starting from 4 for the fourth highest score. The output of the problem is a string array called result, where each element corresponds to the rank of the competitor at the same index in the original score array. This means that once we determine the rankings, we need to map them back to the original order of the input array. The input is an integer array, and the output is the string array with ranks assigned as described. To better understand how the ranking works, let's look at the first example. Here, the input array is score equals 5, 4, 3, 2, 1. The scores, when sorted in descending order, are 5, 4, 3, 2, 1. The top score, 5, gets the rank gold medal. The second highest score, 4, gets silver medal. The third highest score, 3, gets bronze medal. For the fourth and fifth highest scores, 2 and 1 respectively, we assign their ranks as 4 and 5. The final output array is gold medal, silver medal, bronze medal, 4, 5. Each rank in the output corresponds to the same index as the original score array, ensuring that we preserve the order of the competitors. Now, let's examine another example with input score equals 10, 3, 8, 9, 4. After sorting the scores in descending order, we get 10, 9, 8, 4, 3. The highest score, 10, is assigned gold medal. The second highest score, 9, gets silver medal, and the third highest, 8, gets bronze medal. For the fourth and fifth highest scores, 4 and 3, we assign their ranks as 4 and 5 respectively. When we map these ranks back to the original input order, the output becomes gold medal, 5, bronze medal, silver medal, 4. This demonstrates how the ranks are assigned based on the scores and then reordered to match the original indices of the competitors. Now consider the simplest case with only one competitor, where score equals 1. Since there is only one score, that competitor automatically gets the rank gold medal. The output in this case is simply gold medal. This example highlights how the solution handles the scenario where the input array has just a single element. Additionally, the constraints ensure that all scores are unique, so we don't have to handle ties or duplicate values in any of these cases. Finally, there are a few important constraints and edge cases to keep in mind. The input array score can have anywhere between 1 and 10,000 elements, so our solution must handle larger inputs efficiently. Each score in the array is a non-negative integer within the range of 0 to 1 million, and all scores are guaranteed to be unique. Some edge cases to consider include when there is only one competitor, where the output is always gold medal, or when the scores are given in ascending order, meaning the algorithm must correctly sort them in descending order first. Additionally, if the scores are already in descending order, the ranks correspond directly to their indices. Handling the maximum input size efficiently is critical to ensure the solution meets performance requirements within the given constraints. To solve the relative ranks problem, we can start by considering a brute force approach. The intuition here is simple: sort the scores in descending order so that the highest scores come first, and then manually assign ranks based on this sorted order. For the top 3 scores, we use predefined labels like gold medal, silver medal, and bronze medal, while the rest are assigned numerical ranks starting from 4. The process involves creating a copy of the input array, sorting it, and then using the sorted array to map each score to its rank in the original array. This approach is straightforward and easy to implement, but it comes with trade-offs. Since sorting the array takes n log n time and additional space is needed for the copy, it's not the most memory-efficient solution. While it works well for small datasets, it's worth exploring if we can optimize further, especially for scenarios where sorting can be avoided or simplified with better data structures. Building on the brute force idea, an optimized approach involves sorting with index tracking. Instead of creating a separate copy of the scores, we pair each score with its original index as a tuple. By sorting these tuples in descending order based on the scores, we can directly map the ranks back to their original indices in the input array. This removes the need for a full array copy, saving memory. After sorting, the top 3 scores are assigned metal labels, and the remaining scores are given numerical ranks. This approach maintains an O(n) log n time complexity due to sorting, but it is more memory efficient than the brute force method. It's a practical solution, especially for competitive programming scenarios, as it reduces unnecessary overhead while still being easy to implement and understand. An alternative approach uses a heap, or priority queue, to manage the scores. With a max heap, we can efficiently retrieve the highest scores along with their indices. The process involves building the heap, which takes O(n), and then repeatedly extracting the top element to assign ranks. Once all ranks are determined, we map them back to the original array. While the overall time complexity remains O(n) log n, this method introduces higher constant overhead due to the additional complexity of heap operations. It's less intuitive and more cumbersome compared to sorting-based methods. This approach might be worth considering in specific scenarios where heap operations are inherently required, but for this problem, it's generally not the most practical solution. After evaluating the different approaches, the optimized sorting method with index tracking stands out as the best strategy. Sorting is essential to determine the relative ranks, and by pairing scores with their indices, we streamline the process of mapping ranks back to the original array. This minimizes extra space usage while maintaining an optimal O(n) log n time complexity. The simplicity of this approach makes it easy to implement and reduces the likelihood of errors. Additionally, it scales well for a wide range of input sizes, handling competition scenarios efficiently without significant overhead. While it's not a linear solution, the balance between time complexity and implementation simplicity makes it the most practical choice. Overall, this method ensures efficiency, maintainability, and clarity, which are key for solving the relative ranks problem effectively. To solve the problem of assigning ranks to a list of scores, we need to ensure that the highest score gets labeled as gold medal, the second highest is silver medal, the third highest is bronze medal, and all other scores are assigned numeric ranks in descending order of their values. We'll begin by validating the input to make sure it's a non-empty list of integers. If the list is empty, we simply return an empty list. Next, since the ranks must be assigned to the original order of scores, we'll pair each score with its original index by creating a list of tuples where each element consists of the score and its corresponding index. For example, given the scores 10, 3, 8, 9, 4, we would create the list 10, 0, 3, 1, 8, 2, 9, 3, 4, 4. This setup allows us to keep track of the original positions of the scores as we process them further. Once the scores are paired with their original indices, the next step is to sort the tuples in descending order based on the scores. We can achieve this efficiently using Python's built-in sorted function with a custom key that sorts by the score value. For instance, sorting the list 10, 0, 3, 1, 8, 2, 9, 3, 4, 4 results in the sorted list 10, 0, 9, 3, 8, 2, 4, 4, 3, 1. After sorting, we assign ranks to the scores based on their positions in the sorted list. The highest score, which is the first element, is assigned the rank gold medal. The second highest score gets silver medal, and the third highest score gets bronze medal. Any remaining scores are assigned numeric ranks starting from 4 and increasing sequentially. For this example, the ranks would be gold medal, silver medal, bronze medal, 4, 5. Finally, we need to restore the ranks to the original order of the scores. Using the original indices stored in the tuples, we map these calculated ranks back to their respective positions in the original list. The final step is to return the list of ranks in the order corresponding to the original input list. For the example scores 10, 3, 8, 9, 4, after restoring the ranks to their original indices, the result would be gold medal, 5, bronze medal, silver medal, 4. This approach highlights some key insights. First, sorting the scores simplifies the ranking process significantly, as the order of ranks directly corresponds to the sorted order. Second, preserving the original indices is crucial for correctly mapping the calculated ranks back to the original positions. Without this step, restoring the order would be difficult. Finally, handling the top 3 scores with special labels like gold medal rather than numeric ranks requires careful attention during rank assignment. The use of a list of tuples to pair scores with their indices and a separate result list for ranks are central to solving this problem efficiently. Analyzing the time complexity of this algorithm, sorting the scores requires O, an asterisk log, n, time, as the sorted function is based on an efficient comparison sort. Assigning ranks involves iterating through the sorted list, which takes O, n, and restoring the ranks to their original order also takes O, n. Therefore, the overall time complexity is dominated by the sorting step, resulting in O, n asterisk log, n. For space complexity, the list of tuples used to store scores and their indices requires O, n, space, and the result list for ranks also takes O, n, space. Thus, the total space complexity is O, n. Now, let's consider some edge cases. If the input list is empty, the algorithm simply returns an empty list. If all scores are equal, their sorted order remains unchanged, so they are assigned sequential numeric ranks without any special handling. For a single score, the algorithm directly assigns it the gold medal, as it's the only element in the list. These cases ensure the algorithm works correctly in a variety of scenarios. To solidify our understanding, let's walk through a complete example. For the input scores 10, 3, 8, 9, 4, we first pair each score with its original index, resulting in 10, 0, 3, 1, 8, 2, 9, 3, 4, 4. Sorting these tuples by score in descending order gives 10, 0, 9, 3, 8, 2, 4, 4, 3, 1. Next, we assign ranks based on their positions in the sorted list. The first score gets gold medal, the second gets silver medal, the third gets bronze medal, and the remaining scores are assigned numeric ranks, resulting in gold medal, silver medal, bronze medal, 4, 5. Finally, using the original indices, we restore these ranks to their respective positions in the input list, yielding the output gold medal, 5, bronze medal, silver medal, 4. This example demonstrates the algorithm's steps in action, from input validation to final output, and highlights how each part of the process contributes to solving the problem effectively. This code solves LeetCode problem number 506, relative ranks, by assigning ranks to scores based on their descending order. Let's break it down step by step. 1. Sorting with indices, we first pair each score with its original index using the enumerate function. This allows us to track the original position of each score after sorting. We then sort this list in descending order of scores using the sorted function with a custom key. 2. Result initialization, we create a result list of the same size as the input scores list. This list will store the ranks or medals for each athlete, indexed by their original position. 3. Rank assignment, we iterate through the sorted scores. For the top 3 scores, we assign gold medal, silver medal, and bronze medal, respectively. For the remaining scores, we assign their rank as a string, rank starts at 1, so we add 1 to the 0-based index. For return results, finally, the result list, which now contains the ranks or medals in the original order of input scores, is returned. This approach leverages sorting and indexing effectively, ensuring a time complexity of O, n log n, due to the sorting step. The rest of the operations, such as initialization and rank assignment, are linear in complexity, making this solution efficient and easy to understand. Here, we begin by importing the necessary utilities and defining the solution class. The goal is to implement the findRelativeRanks method, which takes an array of scores as input and returns a string array representing the ranks of each athlete. First, we determine the length of the scores array and create a two-dimensional array, score index pairs, to store each score along with its original index. This allows us to keep track of the positions of the scores after sorting. Next, we iterate through the scores array and populate score index pairs with the score at position 0 and its corresponding index at position 1. After that, we sort the score index pairs array in descending order based on the scores. This is done using the arrays.sort method with a custom comparator that subtracts the first score from the second, effectively prioritizing higher scores. After sorting, we create a result array of strings to store the ranks, which we'll assign in the next steps. After preparing the result array, we use a loop to assign ranks based on the sorted order of scores. For the first 3 athletes, we assign special ranks: gold medal for the highest score, silver medal for the second highest, and bronze medal for the third. This is done using simple if-else conditions that check the current rank index. For all other athletes, their rank is assigned as a string representing their position, which is calculated as rank plus 1 because ranks are 1-based. The original index of each score, stored in score index pairs, helps us place the rank in the correct position of the result array. Finally, once all ranks have been assigned, the result array is returned, completing the implementation. This method efficiently handles the ranking process while preserving the original order of the input scores in the output. Let's start with example 1, where the input scores are 10, 3, 8, 9, 4. First, we pair each score with its original index to keep track of their positions: 0, 10, 1, 3, 2, 8, 3, 9, 4, 4. This allows us to know where each score belongs in the final output, even after sorting. Next, we sort these pairs by the scores in descending order. The result is 0, 10, 3, 9, 2, 8, 4, 4, 1, 3, where the highest score comes first. After sorting, we initialize a result array of the same size as the input, filled with empty strings, comma, 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 comma. This array will eventually hold the ranks for each score in the correct positions. Now, we assign ranks to the scores based on their positions in the sorted list. The highest score, which is at index 0 of the sorted list, gets the gold medal. We look at the original index of this score, which is 0, and assign gold medal to result 0, giving us gold medal, comma, comma, comma. Next, the second highest score, at index 3 in the sorted list, gets the silver medal, so we update result 3 to silver medal, resulting in gold medal, comma, silver medal. The third highest score, at index 2, gets the bronze medal, which updates result 2 to bronze medal, resulting in gold medal, bronze medal, silver medal. For the fourth rank, we convert 3 plus 1 to 4 and assign it to result 4, giving us gold medal, bronze medal, silver medal, 4. Finally, the fifth rank is converted to 5 and assigned to result 1, yielding the final output, gold medal, 5, bronze medal, silver medal, 4. In example 2, where all scores are identical at 5, the input is 5, 5, 5. First, we pair the scores with their indices 0, 5, 1, 5, 2, 5. Since all scores are the same, sorting does not change the order, so the sorted result remains 0, 5, 1, 5, 2, 5. Then, we initialize the result array with empty strings, comma, comma. For rank assignment, the highest ranked score, at index 0, gets the gold medal, updating result 0 to gold medal, resulting in gold medal, comma. The next score, at index 1, gets the silver medal, so result 1 is updated to silver medal, giving us gold medal, silver medal. Finally, the third score, at index 2, gets the bronze medal, updating result 2 to bronze medal. The final output for this example is gold medal, silver medal, bronze medal. In example 3, we have a single score of 42 as the input, so the process is straightforward. The initial pair is 0, 42, and since there's only one element, the sorted result remains 0, 42. We then initialize a result array with a single empty string. Since this is the only score, it automatically receives the highest rank, the gold medal. We assign this to result 0, resulting in gold medal. This example highlights that even for a single element, the process works consistently. A few key observations can be made from these examples. Sorting the scores helps determine their relative order efficiently, while keeping track of their original indices ensures that ranks are placed correctly in the result array. Additionally, the top 3 ranks are labeled with gold medal, silver medal, and bronze medal, while all other ranks are assigned numeric labels increment by 1. The time complexity of our solution is influenced by 3 main operations. First, we sort the scores along with their original indices using the sorted function. In Python, sorting a list of length n has a time complexity of n log n. This is because the sorting algorithm, timsort, is optimized for real-world data but still requires this complexity in terms of comparisons and rearrangements. Next, we initialize the result array with placeholders using *len scores. This step is straightforward and takes linear time, or n, as it scales with the size of the input. Finally, we assign ranks by iterating over the sorted list using the enumerate function. For each score, we determine its rank and place the corresponding value in the result array. This final operation also takes linear time, or O(n), since we process each element exactly once. These three steps together define the overall time complexity of the solution. When we analyze the total time complexity, the sorting step, which is O(n log n), is the most computationally expensive operation and dominates the overall runtime. The initialization of the result array and the rank assignment steps, both of which are O(n), are relatively minor in comparison. Adding these together, the overall time complexity remains O(n log n). Now, turning to space complexity, we consider both the input storage and auxiliary storage. First, the input list scores itself requires O(n) space since it holds n elements. Additionally, the sorted list, which temporarily stores tuples of indices and scores, also takes up O(n) space. Finally, the result array, where the ranks are stored, contributes another O(n) to the space complexity. These are the key contributors to the memory usage of our solution. Another factor to consider in space complexity is the sorting overhead. Python's sorted function uses timsort, which may require additional memory for temporary buffers during the merge operations. In the worst case, this auxiliary memory usage is also O(n). Putting it all together, the dominant space contributors are the input list, the sorted list, the result array, and the sorting overhead. Summing these, the overall space complexity is O(n). Now let's analyze the solution in different scenarios. In the best case, even if the input list is already sorted in descending order, the sorted function still processes the entire list and takes O(n log n) time. Similarly, in the average case, which assumes random input, the sorting step remains the dominant operation, leading to a time complexity of O(n log n). Finally, in the worst case, the sorting step still dictates the runtime, making the worst case complexity identical to the best and average cases at O(n log n). To put this into perspective, let's compare the optimized solution with a naive approach. A naive method might involve repeatedly finding the maximum score from the list and assigning ranks iteratively. This approach would result in a time complexity of O(n squared, because finding the maximum in an unsorted list is a linear operation, and we would need to repeat this process for all n elements. In contrast, our optimized solution uses efficient sorting, which takes O(n log n, and combines it with a single traversal for rank assignment, which is O(n). This significant improvement makes the solution optimal, as sorting is an unavoidable step when determining ranks accurately. In conclusion, the given solution achieves the best possible efficiency with a time complexity of O(n log n and a space complexity of O(n). These characteristics make it well suited for handling large inputs, such as lists with up to 10,000 elements. When solving the relative ranks problem, there are several common mistakes to be aware of. First, it's easy to assume that all scores are unique, but this may not always be the case. If scores are duplicated, directly assigning ranks based on their index in a sorted list will result in errors. Always ensure that duplicates receive the same rank. Another pitfall is incorrectly adjusting ranks for ties. For example, if two players share the second rank, the next rank assigned should be the fourth, not the third. This ensures that ranking gaps are properly accounted for. Additionally, modifying the original input list during sorting can lead to unintended consequences, such as losing access to the original data. Instead, create a copy of the input before sorting. Inefficient sorting methods can also become a problem for large inputs. While general-purpose sorting algorithms work well in most cases, if the score range is small, counting sort or hash maps can offer significant performance improvements. Finally, don't overlook edge cases. Scenarios like an empty input list, a single score, or all scores being the same should be tested to ensure your solution is robust and handles these gracefully. For interviews, there are several key insights to keep in mind when tackling problems like relative ranks. First, always clarify constraints with your interviewer. Ask whether scores are integers or floating point, how to handle ties, and what edge cases you should consider. This ensures your solution aligns with the problem's requirements. If the input size is large, you should also discuss optimization strategies early. For instance, bucket sort or rank assignment using a hash map can be more efficient than traditional sorting. It's also important to communicate trade-offs between time complexity and code simplicity. While a brute force sorting approach might be quick to implement, it may not scale effectively for larger datasets. Using clear and descriptive variable names, like rank or sorted underscore scores, is another important tip to make your code easier to follow during interviews. Finally, always test your solution with a variety of custom cases, including edge cases and stress tests. This demonstrates not only the robustness of your solution but also your attention to detail and thoroughness. The relative ranks problem shares similarities with several other problems, which can help broaden your understanding. For instance, LeetCode 1337, the k weakest rows in a matrix, involves ranking logic similar to this problem. LeetCode 973, k closest points to origin, focuses on sorting with custom criteria, while LeetCode 703, kth largest element in a stream, uses heap-based ranking, which can be an alternative approach for certain scenarios. Of course, LeetCode 506, relative ranks, remains the most directly related example. As for alternative approaches, you can use a hash map combined with sorting. Here, you store scores as keys and indices as values, sort the scores, and then assign ranks. This avoids modifying the original list but adds some implementation complexity. Counting sort is another option for cases with a limited score range. It's highly efficient with O(n) complexity but can be memory intensive for larger ranges. Lastly, a heap-based ranking approach allows you to extract the highest scores iteratively and assign ranks as you go. While this is particularly useful for top K ranking scenarios, it's less efficient for assigning ranks to all elements, with a complexity of O(n) log k. Great job today! We explored the relative ranks problem and walked through a straightforward yet effective solution. Make sure to practice similar problems to reinforce these concepts. Thank you for watching, and I'll see you in the next session. Don't forget to like and subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!